Tonight, we're going to leave Earth behind, slowly, deliberately, one boundary at a time, and I want you to notice something as we go. At the beginning of this journey, you will feel almost nothing has changed. The sky will still look blue from where you're floating. The Earth will still be close enough to fill your window. You could, in theory, come home in an afternoon, but somewhere in the hours that follow, without any single dramatic event, the universe is going to start taking things away from you. Not violently, not all at once. Quietly, the way a tide goes out. First the magnetic field that has been guarding you since before you were born. Then the light that has warmed every living thing that has ever existed. Then the voice of Earth in your radio, which will grow fainter and further delayed until it disappears into silence that lasts for years. Then, eventually the sun itself, reduced to a single indistinguishable point of light in a black field of countless others just like it. This is the real story of what happens as you travel further into space. It is not a story about monsters or hostile aliens or forces that reach out to hurt you. It is a story about subtraction, about how much unseen protection surrounds a human being standing on the surface of the Earth, and about how far you would have to travel before you understood, all at once, exactly how much of that protection you had been taking for granted. By the end of tonight, you will understand exactly what is lost at each stage of a journey outward, from the edge of our atmosphere to the edge of everything that can ever be seen, and why the danger of distance was never really about monsters at all. If you enjoy journeys like this one, take a moment to like this video or subscribe. It helps more than you'd think, and it lets us keep making these late night trips together. Now, let's begin. Start at 400 kilometers above the surface of the Earth, which is roughly 250 miles, which is about the distance from New York City to Pittsburgh, except straight up instead of sideways. This is where the International Space Station orbits, circling the planet once every 90 minutes, moving at roughly 28,000 kilometers an hour, which is about 17,500 miles an hour. Fast enough that the astronauts on board see a sunrise and a sunset every 45 minutes. In a single 24-hour day, an astronaut aboard the station experiences 16 full sunrises and 16 full sunsets, a rhythm so far removed from anything the human body evolved to expect that astronauts often describe losing their sense of day and night within the first week, relying entirely on the station's clock rather than the light outside the window to know when to sleep. At this altitude, space already looks like space. The sky is black, the stars don't twinkle because there's no atmosphere left to make them shimmer, no turbulent air to bend and scatter their light the way it does for someone standing on the ground looking up. And yet, for all of that visual drama, the astronauts up there are still, in the most important sense, still home. They are still deep inside Earth's magnetosphere, the vast invisible bubble generated by the churning molten iron in our planet's core. A bubble that extends tens of thousands of kilometers out into space in every direction and deflects the overwhelming majority of the charged particles that the sun throws at us every single second. Without that bubble, the solar wind, a constant stream of protons and electrons blasting outward from the sun at speeds of hundreds of kilometers per second, would slowly strip away our atmosphere the way it has stripped away the atmosphere of Mars. With it, that same wind, is deflected around us like water around the hull of a ship, and the radiation that reaches the surface of the Earth is a small, survivable fraction of what exists just a few hundred kilometers higher up. This is the first thing worth sitting with before we go any further. The astronauts on the International Space Station are not actually experiencing space in the way we imagine it when we say the word. They are experiencing a heavily filtered, carefully shielded version of it, floating inside a magnetic cocoon that most of us never think about because we have never had reason to. Every person who has ever lived, every plant, every animal, every single living cell on this planet has existed entirely within that cocoon. It is so completely a part of the background of life on Earth that it doesn't even register as a form of protection. It just feels like the ordinary way things are. And that is exactly the pattern we are going to see over and over again tonight as we move further out. The protections that feel like the ordinary way things are turn out to be extraordinary, specific, and finite. And once you leave them behind, they do not come back on their own. They have to be replaced artificially at enormous cost by anyone who wants to survive without them. There is a second layer of protection at this altitude that rarely gets discussed, and it has nothing to do with radiation. It is the simple, physical presence of pressure. The human body is built to function inside a fairly narrow range of atmospheric pressure, and the moment you leave that range without a pressurized suit or a pressurized cabin, the consequences are almost immediate. At the edge of space, unprotected exposure doesn't cause the body to freeze solid or explode the way older films sometimes suggested. What actually happens is more insidious. The moisture on your tongue and in your eyes would begin to boil, not because of heat, but because of the drop in pressure, a phenomenon called ebulism. Consciousness would be lost within about 15 seconds as the oxygen is pulled out of your blood. Every single layer of engineering on the International Space Station, every seal, every gasket, every centimetre of hull, exists to hold back this reality, to maintain artificially the one narrow band of pressure that a human body actually requires to remain alive. There is one more kind of protection worth naming before we leave low Earth orbit behind, and it isn't physical at all. It's psychological, and it turns out to be just as real, just as measurable as anything involving radiation or pressure. For decades, scientists interested in understanding the mental toll of long-duration spaceflight have studied close analogues here on Earth, places where small groups of people are isolated together, cut off from ordinary contact with the rest of humanity, for extended periods. Antarctic research stations are one of the most studied examples. During the long polar winter, staff at stations like the American Amundsen Scott South Pole Station or the French-Italian Concordia Station can go months without a single flight, in or out, completely isolated by weather that makes evacuation impossible, living under skies that are either continuously dark or continuously light depending on the season, with a small fixed group of the same faces, day after day for as long as 9 months at a stretch. Researchers studying these crews have documented a real, recurring set of psychological effects, sometimes called winter over syndrome, including irritability, difficulty concentrating, disrupted sleep, and a kind of emotional flattening that tends to set in around the midpoint of the isolation period, regardless of how carefully the individuals were screened beforehand. NASA and other space agencies have taken this seriously enough to fund direct simulations of Mars-length missions here on Earth. In an experiment called Mars 500, conducted between 2010 and 2011, a crew of 6 volunteers spent 520 consecutive days sealed inside a windowless facility outside Moscow, simulating the full round-trip duration of a real crewed Mars mission, including a communication delay artificially built into every message sent to or from mission control. Even knowing at every moment that they could open a door and leave, that no radiation or vacuum was actually threatening them, the crew still experienced measurable psychological strain, including at least one participant later reported to have experienced depression significant enough to affect his engagement with the mission, and researchers noted a broader pattern of crew members gradually withdrawing from one another and becoming less physically active as the isolation dragged on. This is worth sitting with, because it means that even in a scenario with zero actual physical risk, the human mind still responds to sustained isolation, artificial time delay, and the absence of the ordinary sensory world, sunlight, weather, the presence of strangers, in ways that measurably resemble the stress responses seen in genuine survival situations. Distance, it turns out, doesn't have to be real to change you. It only has to feel real, sustained for long enough, for the mind to start treating it as a genuine threat. This matters enormously for everything that follows tonight, because every stage of the journey we're about to take doesn't just strip away physical protections one at a time. It also strips away the ordinary psychological scaffolding of human life. The sunrise and sunset, the conversation that arrives within a second of being spoken, the crowd of strangers, the weather, the weight of gravity pulling consistently in one direction. Long before an astronaut's body would ever be harmed by radiation from beyond the heliopause, the astronaut's mind would already be contending with a kind of isolation no human being evolved to withstand. An isolation measured not in radiation dose, but in the sheer, accumulating weight of sameness, silence, and distance from anyone who isn't already in the room with you. Researchers who study these effects sometimes describe a phenomenon called sensory monotony, a state in which the mind, deprived of the ordinary variety of stimulation it expects, from changing light to changing faces to changing weather, begins to generate its own internal noise to compensate, which can manifest as anything from vivid, unusually memorable dreaming to difficulty distinguishing one day from the next, a blurring of time that several returning space station crew members have described in post-mission interviews, noting that entire weeks aboard the station sometimes felt, in retrospect, like a single continuous day. There is one more form of protection worth naming here, one so constant and so fundamental that it barely occurs to most people to think of it as a protection at all: gravity itself. The human body did not evolve in the absence of it. Every system inside you, your bones, your muscles, your cardiovascular system, your inner ear, developed over millions of years under the constant, unchanging pull of Earth's surface gravity, and every one of those systems begins to change, measurably and sometimes seriously, the moment that pull is removed. Astronauts aboard the International Space Station, floating in what's often loosely called zero gravity, but is more accurately described as continuous freefall, lose bone density at a rate of roughly 1 to 1.5% per month in weight-bearing bones, a rate of loss comparable to, or in some cases faster than, the bone loss experienced by elderly patients with osteoporosis here on Earth, except compressed into a fraction of the time. Muscles that no longer have to work against gravity begin to atrophy within days, which is why astronauts aboard the station are required to exercise for roughly 2 hours out of every single day, using specially designed resistance machines just to slow, not stop, the loss of muscle and bone mass. Even with rigorous daily exercise, astronauts returning from long-duration missions typically require weeks of physical rehabilitation on Earth simply to safely walk, stand, and support their own body weight again, muscles and bones having partially forgotten, in the span of months, a job they had done automatically for an entire lifetime. There's a subtler effect as well, discovered more recently, that illustrates just how deeply the body assumes gravity will always be present. On Earth, gravity pulls bodily fluids downward toward the legs constantly, which is why your face doesn't look puffy in the morning, and your legs sometimes do by the end of a long day standing up. In microgravity, that downward pull disappears, and fluids that would normally settle in the lower body instead shift upward toward the head and chest. This fluid shift is believed to be a major contributing factor to a condition NASA calls Spaceflight-Associated Neuroocular Syndrome, or SANS, first identified through a pattern of astronauts returning from long-duration missions with measurable changes in the shape of their eyeballs and the structure of the optic nerve, in some cases leading to lasting changes in vision. It remains one of the most actively studied medical risks of long-duration spaceflight, precisely because it wasn't something anyone predicted in advance. It was something the human body revealed about itself only once it was actually removed, for months at a time, from the one force that had shaped its development since before recorded history began. All of this matters enormously for anything resembling a real journey outward, because it means the body carrying you further into space is not a fixed, stable vehicle. It is a system that has spent its entire evolutionary history calibrated to a very specific set of earthbound conditions, and every one of those conditions, gravity included, is itself a kind of invisible scaffolding, holding your biology together in ways you never had to think about, right up until the moment it's taken away. Let's go further. Beyond the space station, beyond low Earth orbit, there is a region of space that most people have never heard of, even though it was discovered decades before human spaceflight existed at all. In 1958, a physicist named James Van Allen, working with data from the earliest American satellites, discovered 2 enormous donut-shaped regions of intense radiation encircling the Earth, now known as the Van Allen radiation belts. The inner belt begins around 1,000 kilometers above the surface and extends out to about 6,000 kilometers. The outer belt begins around 13,000 kilometers and can extend as far as 60,000 kilometers from Earth, depending on solar activity. These belts are made of high-energy charged particles, trapped and accelerated by Earth's magnetic field, whipping back and forth between the planet's magnetic poles at speeds close to the speed of light. To pass through them unshielded for any significant length of time would deliver a lethal dose of radiation to a human body. This is not a hypothetical danger dreamed up for a documentary. It is a real, physical hazard that every single Apollo mission had to calculate for, plan around, and pass through as quickly as possible on the way to the moon. Spending only a matter of minutes inside the most intense regions, timed carefully to minimize exposure. Think about that for a moment. The very first time human beings left the protective bubble of Earth's lower magnetosphere, they had to physically punch through a belt of trapped, lethal radiation just to get clear of the planet. And once they were clear of it, once the Apollo astronauts continued out past the belts toward the moon, something happened to them that has happened to a total of 24 human beings in all of history. And to no one else, ever, they left the protection of Earth's magnetic field completely, for the roughly 3 days it took to coast from Earth to the moon. Those 24 astronauts were the only human beings who have ever been fully exposed to the unfiltered radiation environment of deep space outside of Earth's magnetosphere for any extended period of time. Every other human being in history, every astronaut on the space station, every satellite technician, every person watching this video right now has spent their entire life inside that bubble. The Apollo astronauts are the only exceptions we have ever produced as a species, and even they were only outside it for a matter of days, not years. The moon itself sits at an average distance of about 384,000 kilometers from Earth, which is around 239,000 miles. If you try to drive that distance by car at a steady 100 kilometers an hour, without ever stopping to sleep, eat or refuel, it would take you about 160 days. The Apollo spacecraft covered it in roughly 3 days, which tells you something about how fast they were actually moving. And yet from the perspective of someone standing on the moon's surface, looking back, the Earth was still close enough to see whole. The entire planet, every ocean, every continent, every person who has ever lived or died, fit inside a disk you could cover with your thumb held at arm's length. The Apollo astronauts described this as one of the most profound moments of their lives. This first true outside view of the whole Earth, small and blue and finite, hanging alone in blackness. The astronaut Edgar Mitchell, who walked on the moon during the Apollo 14 mission, described looking back at Earth on the return journey and experiencing what he later called a profound shift in awareness, a sudden, overwhelming sense that everything he had ever known, every conflict, every border, every argument, was happening on a single small object floating in blackness, with no visible lines separating one nation from another. This experience became so common among astronauts who saw Earth from a distance that researchers eventually gave it a name: the overview effect, a well-documented psychological shift toward feelings of unity, fragility, and perspective. Triggered specifically by seeing the whole planet at once, from far enough away to comprehend it as a single object rather than a collection of separate places. It is the same feeling the astronomer Carl Sagan captured decades later when he convinced NASA to turn the Voyager 1 spacecraft around from billions of kilometers away, just to take one photograph of Earth as a single pale point of light suspended in a sunbeam. Sagan later wrote about that image, describing Earth as a tiny stage in a vast cosmic arena, the only home we have ever known. And the emotional core of what he was reaching for was not fear, it was perspective. And that distinction between fear and perspective is one we are going to need to hold on to carefully as we keep moving outward tonight, because the two things can look very similar from a distance, and it matters which one you're actually feeling. At the distance of the moon, communication with Earth still happens almost instantly. delayed only by about 1 1/3 seconds each way, the time it takes light, and therefore radio waves, to cross that distance. You speak, and a little over a second later, Mission Control hears you. They respond, and a little over a second later, you hear them. It's a noticeable delay, but a conversational one. You could still, in a real sense, have something resembling a normal conversation with home. This is a detail worth keeping in mind, because it's the last stop on this entire journey where that will be true. Before we leave the inner solar system entirely, it's worth pausing at a planet that rarely gets the attention it deserves, precisely because it sits so close to us, and yet represents one of the most hostile environments anywhere in our neighbourhood of the solar system. Venus is, on paper, Earth's closest twin in terms of size, mass, and composition, roughly the same diameter, formed from similar material, orbiting at a distance that isn't drastically different from our own. And yet the surface of Venus is the most lethal place a human being could stand in the entire solar system, more hostile even than the vacuum of open space in some very specific ways, because vacuum at least does not actively crush you. The surface pressure on Venus is roughly 92 times that of Earth, equivalent to the pressure found nearly a kilometre deep in Earth's oceans. A human being standing unprotected on the Venusian surface would be crushed by that pressure alone within seconds, even before accounting for anything else. The surface temperature averages around 464 degrees Celsius, roughly 867 degrees Fahrenheit, hot enough to melt lead, and this temperature barely varies between day and night, or between the equator and the poles, because Venus's atmosphere, composed of roughly 96% carbon dioxide, traps heat so efficiently that the entire planet has become a single uniform furnace. The atmosphere itself contains clouds of sulfuric acid, and the pressure at the surface is thick enough that, according to data gathered by Soviet Venera landers in the 1970s and 1980s, several of the spacecraft sent to study the surface directly survived only a matter of minutes, some less than an hour, before being crushed, cooked, or corroded into silence. To date, Venus remains the only planet other than Earth on which a human-made object has successfully landed and transmitted images back before being destroyed, and every single one of those missions ended the same way, with the harshest surface conditions in the solar system slowly overwhelming and disabling the spacecraft, one system at a time. The lesson Venus teaches us is subtle, but important for understanding the rest of tonight's journey. Danger in space does not scale neatly with distance. Venus is, on some measurements, closer to Earth than Mars ever gets, and yet it is dramatically less survivable. Distance is one axis of difficulty, but it is not the only one, and as we continue outward, we're going to find both kinds of danger. The danger that comes from raw distance and isolation, and the danger that comes from the specific, local conditions of wherever you happen to find yourself. Now let's continue outward, past Earth, past the Moon, past Venus, to the planet most often discussed as humanity's next real destination, Mars. Mars orbits the Sun at a distance that varies enormously depending on where both planets are in their orbits, ranging from about 54 million kilometres at its closest possible approach to Earth to over 400 million kilometres when the two planets are on opposite sides of the Sun. On average, a one-way radio signal between Earth and Mars takes somewhere between 3 and 22 minutes to arrive, depending on the current alignment. This means a real-time conversation with Mars is not just difficult, it is physically impossible, no matter how advanced your technology becomes, because the delay is not a limitation of engineering, it is a limitation of the universe itself. Nothing, as far as we currently understand physics, can carry information faster than the speed of light. If you were an astronaut on Mars and something went wrong, and you radioed for help, the fastest possible response from Earth, even if the message were answered the instant it arrived, could take anywhere from 6 minutes to nearly 44 minutes round trip. In an emergency, that gap is the difference between a discussion and a monologue. You are, for the very first time on this journey, meaningfully alone in a way that has nothing to do with physical distance from other people, and everything to do with the impossibility of a two-way conversation happening in anything resembling real time. There is a particularly unsettling detail buried inside this communication delay that mission planners have had to design around explicitly. During certain periods of the Mars-Earth orbital cycle, called solar conjunction, Mars passes almost directly behind the Sun as seen from Earth, and the Sun's own energetic output interferes catastrophically with radio transmission between the two planets. During these windows, which last for roughly 2 weeks and occur approximately every 26 months, mission controllers on Earth essentially lose the ability to reliably communicate with anything on or around Mars at all. Spacecraft and rovers are pre-programmed with instructions to carry them safely through this blackout, because for those 2 weeks, there is no meaningful way to reach them. No matter what happens, any human crew present on Mars during a future conjunction would experience something no Apollo astronaut, no space station crew, and no human being in history has ever had to face: a scheduled, predictable, unavoidable communication blackout with their entire home planet, lasting roughly 2 weeks, arriving like clockwork every 26 months for as long as they remained there. Mars also introduces us to a second kind of vulnerability, layered on top of the radiation exposure we've already discussed. Mars lost its global magnetic field somewhere between 3 and 4 billion years ago. Scientists studying the planet, using data from missions like NASA's MAVEN orbiter, launched in 2013 specifically to study the Martian atmosphere's interaction with the solar wind, believe that Mars once had a magnetosphere similar in principle to Earth's, generated by a molten churning core. But Mars is smaller than Earth, roughly half its diameter, and it cooled faster. As its core solidified, the magnetic field it generated weakened and eventually collapsed. Without that field, the Martian atmosphere had nothing to protect it from the solar wind, and over the following billions of years, that thin, unprotected atmosphere was slowly, steadily stripped away into space, particle by particle, until what remained was the cold, thin, almost negligible atmosphere we see today, with an average surface pressure less than 1% of Earth's. MAVEN's measurements suggest that Mars continues to lose roughly 100 grams of atmosphere to space every single second. A slow, ongoing bleed that has been happening for billions of years and continues today. Invisible, constant, and irreversible. This matters enormously for anyone standing on the Martian surface, because it means there is no meaningful magnetic shielding and only a token amount of atmospheric shielding against cosmic radiation. Astronauts on the surface of Mars would be exposed to radiation levels many times higher than anything experienced on Earth, day after day, for the entire duration of any mission. Measurements taken by the Curiosity rover's onboard radiation detector suggests that a human being spending roughly 3 years on the Martian surface, the estimated round-trip duration of a crewed mission including transit time, would accumulate a radiation dose considered to meaningfully increase long-term cancer risk, even with reasonable shielding precautions. It is one of the central, unsolved engineering challenges of any real plan to put human beings on Mars for extended periods. How do you protect a human body for months or years at a time on a planet that has lost the 2 layers of protection Earth still has: its magnetic field and its thick atmosphere? Here is the humbling truth hiding inside that fact. Mars looks, from a distance, like Earth's closest cousin in the solar system. It has seasons. It has a 24-hour and 37-minute day, remarkably close to our own. It has polar ice caps, ancient riverbeds, and evidence of a wetter, warmer past, a past that orbital imaging and rover-based geology, particularly from the Curiosity and Perseverance missions, have confirmed included ancient lakes and river deltas billions of years ago. Of every other world in our solar system, it is the one most often described as the most Earth-like. And yet, the moment you actually stand on its surface, the illusion falls away almost instantly, because Mars is not a slightly colder, slightly redder version of Earth. It is a planet that has already lost the fight Earth is still winning, a planet whose protective shield failed billions of years ago, leaving its surface exposed to the same unfiltered radiation environment that exists everywhere outside a magnetosphere. Mars is not a preview of a livable second home. Mars is a preview of what Earth would eventually become if our own magnetic field ever failed the way Mars's did. There's another kind of isolation worth pausing on here, one that has nothing to do with communication delay or radiation, and everything to do with a question that has haunted astronomers for the better part of a century. In 1950, the physicist Enrico Fermi, discussing the possibility of extraterrestrial civilizations over lunch with colleagues, is said to have asked a simple, disarming question that has since become known as the Fermi paradox. If the universe is so vast and so old and contains so many stars, so many of which we now know host planets, then where is everyone? Our own galaxy alone contains an estimated 100 to 400 billion stars, and thanks largely to NASA's Kepler Space Telescope, which surveyed a single patch of sky between 2009 and 2018, we now know that planets are not rare. Kepler's data suggests that the Milky Way likely contains billions of planets orbiting within their star's habitable zone, the region where temperatures could allow liquid water to persist on a surface. And yet, despite decades of dedicated searching, using radio telescopes to listen for artificial signals, and increasingly sophisticated space telescopes to study the atmospheres of distant worlds for chemical signs of life, we have never detected a single confirmed signal, message, or unambiguous biological signature from anywhere beyond our own solar system. There are many proposed explanations for this silence, none of them proven, all of them worth sitting with for a moment. Some scientists argue that life itself might be common, but that the specific combination of conditions needed for complex technological civilization to arise is extraordinarily rare, a filter so difficult to pass through that even a galaxy full of simple microbial life might produce only a handful of civilizations capable of building a radio telescope, scattered so far apart in both space and time that they might never overlap. Others point back to the sheer scale we've been building all night. Even if a civilization exists 1,000 light years away, and even if it began transmitting deliberately toward us the very moment it developed the technology to do so, we would still be waiting 1,000 years for that signal to arrive, and it would have needed to have already been broadcasting for 1,000 years before we could ever hope to notice. Still others raise a more sobering possibility, sometimes called the Great Filter. The idea that some barrier, either behind us in the distant evolutionary past or somewhere ahead of us, prevents most forms of life from ever surviving long enough to become a visible, spacefaring civilization, and that our own continued existence and progress is not yet proof that we've safely passed through it. None of these explanations can currently be tested with certainty. What can be said with real confidence is that the silence itself is a form of isolation, unlike anything we've discussed so far tonight. One that has nothing to do with distance from Earth and everything to do with distance from anyone else at all. Every hazard we've traced up to this point, radiation, pressure, communication delay, has assumed there is still a home to be isolated from, still a civilization back on Earth waiting at the other end of a very long signal. The Fermi paradox raises a colder, quieter question underneath all of that. What if, at the largest scale of all, there simply isn't anyone else out there to eventually reach? What if the loneliness of deep space isn't just about the distance between us and the nearest other star, but about the distance, unmeasured and perhaps unmeasurable, between us and the nearest other mind? Efforts to answer this question directly continue today, largely through radio astronomy projects like the SETI Institute's ongoing survey work, which uses large radio telescope arrays to scan portions of the sky for any signal that couldn't plausibly be explained by a natural astrophysical process, a deliberate pattern, a narrow frequency, something that looks engineered rather than incidental. In over 60 years of organised listening across an ever-expanding portion of the sky and an ever-widening range of frequencies, no such signal has ever been confirmed. This doesn't mean the search has failed, exactly. It means that the portion of the sky and the portion of time that we have actually been able to examine closely remains, even now, a vanishingly small fraction of everything there is to check. One more example, layered on top of everything else tonight, of just how much of the universe still sits entirely beyond the reach of anything we've built so far. Between Mars and the outer planets lies the asteroid belt, and it's worth pausing here for a moment to correct one of the most persistent misconceptions about space travel, because it changes how we should think about danger versus distance. In movies, the asteroid belt is almost always shown as a chaotic minefield, rocks tumbling past each other every few seconds, spacecraft weaving and dodging through a dense field of debris. In reality, the asteroid belt is almost entirely empty space. It contains an estimated 1 to 2 million asteroids larger than 1 kilometre across, along with millions of smaller fragments. But it is spread across a region of space so vast, roughly between 220 and 370 million kilometres from the Sun, that the average distance between any two sizable objects is estimated to be around 1 million kilometres. Every single spacecraft humanity has ever sent through the asteroid belt, including Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and the New Horizons probe, has passed through it without needing to perform a single evasive manoeuvre, without incident, without even a close call. The dwarf planet Ceres, the largest object in the belt, accounts for roughly a third of the belt's entire estimated mass by itself, which gives some sense of just how much emptiness surrounds even its most substantial residents. The danger of the asteroid belt was never really about collision risk. The real lesson the asteroid belt teaches us is about scale, about how easy it is to imagine space as crowded and busy when the truth is closer to the opposite. Space, even in its busiest regions, is defined overwhelmingly by emptiness. Beyond the asteroid belt, we reach Jupiter, and here the danger becomes very real again, though it comes from an entirely different source than anything we've encountered so far. Jupiter has by far the strongest magnetic field of any planet in our solar system, roughly 20,000 times stronger than Earth's, generated by a deep layer of metallic hydrogen inside the planet. Hydrogen compressed under such extraordinary pressure that it behaves like a liquid metal, conducting electricity and generating a magnetic field of staggering scale. That field traps and accelerates charged particles into radiation belts far more powerful than Earth's Van Allen belts so intense that they were a major engineering obstacle for every spacecraft that has ever visited the Jupiter system. The radiation environment around Jupiter's moon Io, one of the innermost large moons, is so severe that a human being standing unshielded on its surface would receive a lethal radiation dose in a matter of minutes. Spacecraft sent to study the Jupiter system, including NASA's Juno mission, launched in 2011, have had to be engineered with thick titanium radiation vaults just to protect their electronics long enough to complete their science missions before the radiation slowly degrades and eventually destroys their instruments, with Juno's own titanium vault, roughly the size of an SUV's trunk, designed specifically to reduce the radiation reaching its onboard computer by a factor of roughly 800. Jupiter's moon Europa, meanwhile, presents a different and stranger kind of danger, precisely because it also represents one of the most compelling targets in our search for life beyond Earth. Beneath Europa's icy shell, scientists believe there exists a liquid water ocean, kept warm not by sunlight, which is far too weak at that distance from the sun, but by tidal flexing. The constant gravitational kneading Europa receives as it orbits within Jupiter's powerful gravitational field. That ocean is thought to contain more liquid water than all of Earth's oceans combined, sealed beneath an ice shell that may be tens of kilometers thick, and radiation levels at the surface are severe enough that any future lander would need significant shielding just to survive long enough to drill down and take a single sample. It's a strange kind of paradox worth sitting with. One of the most promising places in the entire solar system to search for life is also one of the most radioactive, hazardous surfaces we know of. A place where the very same magnetic field that might help protect a potential ocean of life below is the same field making the surface above nearly uninhabitable for us. NASA's Europa Clipper mission, launched in October of 2024, is currently on its way to Jupiter's system to study Europa's ice shell and subsurface ocean in far greater detail than ever before, using repeated flybys rather than a single risky landing, precisely so its instruments can gather years of data while limiting the cumulative radiation exposure that would otherwise slowly destroy them. The same fundamental trade-off between curiosity and radiation that has shaped nearly every mission to the outer solar system. Saturn, further out still, is comparatively gentler, its own magnetic field weaker than Jupiter's, its radiation belts less severe, though still far more intense than anything found near Earth. It was here, in this outer region of the solar system, that both Voyager spacecraft performed some of their most famous flybys in the late 1970s and early 1980s, sending back the first close-up images of Saturn's rings, of Jupiter's storm systems, of the moons Titan and Europa and Io, images that reshaped our entire understanding of the outer solar system in a matter of a few short years. Saturn's moon Titan deserves its own mention here, because it is the only other body in our solar system known to have stable liquid on its surface, not water, but lakes and seas of liquid methane and ethane, kept liquid by surface temperatures around negative 179 degrees Celsius. Titan has weather, rain, rivers, and even a thick, hazy nitrogen-rich atmosphere denser than Earth's own, and yet it remains one of the coldest, strangest, most alien surfaces we have ever imaged in detail, thanks largely to the European Space Agency's Huygens probe, which landed on its surface in January of 2005, sending back images of a landscape carved by liquid on a moon over 1 billion kilometers from the Sun. NASA is currently developing a follow-up mission called Dragonfly, a nuclear-powered car-sized rotorcraft scheduled to launch in the late 2020s and arrive at Titan in the mid-2030s, designed to fly from site to site across the moon's surface, taking advantage of Titan's thick atmosphere and low gravity, only about 1/7 of Earth's, which together make powered flight far easier there than it would be almost anywhere else in the solar system. If successful, Dragonfly would mark the first time humanity has flown a vehicle through the skies of another world beyond Mars, exploring a moon so cold and so strange that its rain is methane, its rivers carve stone at nearly 200 degrees below zero, and its distance from the Sun is so great that a mission taking a decade just to arrive is considered, by the standards of everything we've discussed tonight, remarkably fast. Beyond Saturn lie Uranus and Neptune, the two ice giants of our solar system, worlds so distant and so rarely visited that only a single spacecraft, Voyager 2, has ever flown past either of them. In 1986 and 1989 respectively, and no mission has returned to either world in the decades since. Uranus orbits at nearly 20 times Earth's distance from the Sun, receiving so little sunlight that noon on its surface would look like a deep dim twilight compared to Earth's brightest day. Its axis of rotation is tilted so dramatically, roughly 98 degrees, that the planet essentially rolls around the Sun on its side, giving it seasons that last over 20 years each, with some regions experiencing decades of continuous darkness, followed by decades of continuous light. Neptune, further out still, at roughly 30 times Earth's distance from the Sun, is home to the fastest sustained winds ever recorded in the solar system, reaching speeds of over 2,000 kilometers an hour, powerful enough to circle the entire planet in about 16 hours, driven by an internal heat source that remains only partially understood, since Neptune radiates more than twice as much energy as it receives from the distant Sun. To stand on either world, if such a thing were even possible given that both are gas and ice giants without a true solid surface, would mean existing in a realm of near total darkness, crushing pressure, and temperatures cold enough to freeze most gases we consider ordinary on Earth solid, all illuminated by a sun so distant it would appear as little more than an unusually bright star. Now let's continue outward, past the last of the planets, toward the true edge of the sun's dominion, because it is here that the language we use to describe danger has to change entirely, moving from the specific hazards of individual worlds to something more fundamental about the structure of the solar system itself. Voyager 1 launched on September 5th, 1977. As of today, it is the most distant human-made object in existence, currently more than 24 billion kilometers from Earth, a distance so extreme that a radio signal travelling at the speed of light takes over 22 hours to reach it, and another 22 hours for a response to travel back. A full conversation with Voyager 1, one question and one answer, takes the better part of 2 days to complete. And here is where we cross a boundary that almost no one thinks about, a boundary far more significant in its own way than the orbit of any planet. In August of 2012, Voyager 1 crossed what scientists call the heliopause, the outer boundary of the heliosphere, the vast bubble of charged particles and magnetic field blown outward from our sun by the constant pressure of the solar wind. Inside the heliosphere, the sun is, in a very real sense, still in charge. Its particles dominate the local environment. Its magnetic field pushes back against the rest of the galaxy. But at the heliopause, that pressure finally equalizes against the pressure of the interstellar medium, the thin gas and charged particles that fill the space between star systems, and beyond it, the sun's influence effectively ends. When Voyager 1 crossed that boundary, its instruments detected an immediate and dramatic change. The density of charged particles around the spacecraft jumped by a factor of 40, almost overnight in cosmic terms, as it left the relatively sparse, sun-dominated plasma of the heliosphere and entered the denser, colder plasma of true interstellar space. Voyager 1 had left the solar system in the most meaningful physical sense of that phrase, becoming the first human-made object to do so. Voyager 2 followed in November of 2018, crossing its own heliopause boundary at a slightly different location, and confirming much of what Voyager 1 had found 6 years earlier. Both spacecraft are now travelling through the space between stars, the actual interstellar medium, further from the protective influence of our sun than any human construction has ever been. It's worth understanding, in concrete terms, what this radiation actually does, because the word itself has become so common in casual conversation that its real mechanism is easy to lose sight of. Galactic cosmic rays are not, despite the name, rays of light. They are individual atomic nuclei, mostly protons, stripped of their electrons, accelerated to extraordinary speeds by some of the most violent events in the galaxy, including the shockwaves produced by supernovae, exploding stars whose outer layers are blasted outward at speeds of tens of thousands of kilometers per second. When one of these high-energy particles strikes human tissue, it doesn't simply pass through harmlessly. It collides with atoms inside cells, knocking electrons loose in a process called ionization, and if that collision happens to occur within or near a cell's DNA, it can break the delicate double helix structure that carries the instructions for how that cell functions and reproduces. The human body has robust, evolved mechanisms for repairing this kind of damage under ordinary circumstances, constantly patching small errors and breaks in DNA that occur naturally every single day from sources like ultraviolet light and the low background radiation present even at Earth's surface. The danger posed by galactic cosmic radiation isn't that it introduces some entirely new kind of damage the body doesn't know how to handle. It's that, outside the protection of Earth's magnetic field and atmosphere, the sheer volume and energy of that damage increases dramatically, arriving in a form high-energy heavy particles that is considerably harder for the body's repair mechanisms to fix cleanly, sometimes resulting in Dina breaks that are repaired incorrectly, introducing mutations that, over months and years of accumulated exposure, meaningfully raise the risk of cancer and other long-term health effects. This is the unglamorous, cellular-level reality behind every statistic about radiation exposure we've discussed tonight. Not a dramatic, instantaneous event, but a slow, quiet increase in the odds of something going wrong. One ionized atom, one imperfectly repaired strand of Dina at a time, compounding silently over the full duration of a journey through a region of space no longer protected by the shields we've spent all night describing. This is also precisely why any serious engineering plan for deep space travel puts so much emphasis on shielding, and why that shielding problem is so much harder to solve than it might first appear. Simply adding more mass in the form of metal walls has real limits, partly because launching additional mass into space is extraordinarily expensive, and partly because certain kinds of heavy shielding can actually make the problem worse rather than better. When a high-energy cosmic ray strikes a dense material like aluminum or lead, it can trigger a cascade of secondary particles, sometimes called a shower, that can, in certain configurations, deliver more biological damage to anything behind the shielding than the original particle would have delivered on its own. This is why current research into deep space radiation shielding has increasingly focused on lighter materials rich in hydrogen, like water or specially engineered polyethylene, which tend to absorb and dissipate the energy of incoming particles more gently, without producing the same dangerous secondary particle showers. It remains one of the genuine, unsolved engineering problems standing between where we are tonight and any real, extended human presence beyond the protection of Earth's magnetic field. A problem that has less to do with rockets and fuel than with something far smaller and far stranger. The individual, invisible collision between a single atomic nucleus travelling near the speed of light and a single strand of Dina inside a single cell, inside a body that evolved over millions of years, entirely within a bubble of protection it never had to think about, because it never had to survive without one before. Both spacecraft carry a golden record, a phonograph disc containing sounds and images meant to represent life and culture on Earth. Assembled under the direction of Carl Sagan and a small committee of scientists and artists in 1977, containing greetings in 55 languages, music from cultures around the world, and recordings of natural sounds like wind, thunder, and birdsong. It was never designed with the expectation that it would be found or understood by anyone. It was designed as a message in a bottle, thrown into an ocean so vast that the odds of it ever being discovered are, by any reasonable calculation, close enough to zero to be indistinguishable from it. And yet it travels on regardless, carried by two aging spacecraft that continue to send back a faint trickle of data, using transmitters with roughly the power of a fringe of household light bulbs. So weak by the time the signal reaches Earth that it is picked up only by the enormous dish antennas of NASA's Deep Space Network, and processed using techniques capable of extracting a signal from data fainter than the electrical noise generated by the receiving equipment itself. Both Voyagers are expected to lose the ability to power any scientific instruments by around 2025, as their plutonium power sources, which lose about 4 watts of available power each year through natural radioactive decay, finally fall below the threshold needed to keep any instrument functioning. After that, they will continue to coast, silently, forever, following simple physics, carrying their golden records outward into the galaxy, long after every person who worked on the mission. And every person watching this video tonight is gone. And this is where the danger changes character one more time, becoming something closer to what people imagine when they picture deep space in the abstract. Outside the heliosphere, there is no longer any large-scale magnetic structure pushing back against galactic cosmic rays, the extremely high-energy particles that originate from exploding stars and other violent events elsewhere in the galaxy. Inside the heliosphere, the Sun's magnetic field partially deflects these particles, reducing their intensity by a meaningful amount, a phenomenon scientists refer to as solar modulation. Outside it, that shielding disappears, and the full, unfiltered intensity of galactic cosmic radiation exists everywhere, constantly, with nothing standing between it and anything that travels through it. This is one of the primary reasons why any serious plan for long-duration human travel beyond the solar system, whether to another star or simply deeper into interstellar space, has to grapple with a radiation problem far more severe than anything faced even on the surface of Mars. There is no atmosphere out here to attenuate anything. There is no magnetic field, planetary or otherwise, standing in the way. There is only the particle travelling at close to the speed of light and whatever happens to be in its path. But before we go further out toward the stars, there's one more region of our own solar system we need to sit with, because it reveals something genuinely disorienting about how large our own cosmic neighbourhood actually is, even before we've left it. Beyond the orbit of Neptune, beyond the Kuiper belt, where Pluto and thousands of other icy bodies drift in slow, ancient orbits, there exists a theorized structure called the Oort Cloud, a vast, roughly spherical shell of icy debris believed to surround the entire solar system, extending outward not for millions of kilometers, but for as much as 1 to 2 light years in every direction. To put that in perspective, 1 light year is about 9.46 trillion kilometers, or roughly 5.88 trillion miles. If the Oort cloud extends 2 light years from the Sun, its outer edge would be nearly halfway to the nearest other star system entirely. And here is the truly humbling part. Everything inside the Oort cloud, every object drifting within it, is still gravitationally bound to our Sun. It is still, technically, part of our solar system. Voyager 1, despite having already crossed the heliopause and entered true interstellar space in terms of particle density and magnetic environment, will not actually exit the outer edge of the Oort cloud, will not fully leave the gravitational neighbourhood of our own Sun, for another roughly 300 years to reach its inner edge, and as much as 30,000 years to clear its outer edge completely. The Oort cloud is believed to be the source of most long-period comets, icy bodies occasionally nudged out of their distant, slow orbits by the gravitational influence of passing stars or the combined tidal pull of the rest of the galaxy, sending them on journeys that take them plunging back into the inner solar system after tens of thousands, or even millions, of years of drifting undisturbed in the outer dark. No spacecraft has ever directly observed the Oort cloud. Everything we understand about it comes from indirect evidence, primarily the calculated orbits of the comets it is believed to produce, It remains, in a strange sense, the largest structure in our solar system that we have never actually seen. Sit with that for a moment. The most distant human-made object in existence, travelling continuously since 1977, moving at over 60,000 kilometres an hour, has still not left the gravitational boundary of its own home star system, and will not do so for tens of thousands of years. We have spent this entire journey imagining ourselves crossing enormous distances, from the space station to the moon to Mars, to Jupiter to the heliopause, and by every meaningful measure of scale we understand, all of that distance amounts to a single small step within a solar system so large that its true edge is not a place any human construction has ever come close to reaching. Now let's go further still, because the terror this video is named for doesn't fully arrive until we leave our star system behind entirely and start talking about the space between stars. Let's talk about what actually exists in the space between stars, because empty doesn't fully describe it, and neither does dangerous. Not exactly. The interstellar medium, the thin material that fills the vast gaps between star systems, consists mostly of hydrogen and helium gas at densities so low they are almost impossible to describe using everyday intuition. In the densest regions of interstellar space, you might find perhaps 1 atom per cubic centimetre. In the sparsest regions, that number drops to less than 1 atom per 100 cubic centimetres. By comparison, the air you're breathing right now contains roughly 25 quintillion molecules per cubic centimetre. Interstellar space isn't just emptier than Earth's atmosphere, it is emptier by a factor so large that the comparison starts to break down entirely. It is, by any practical human measure, a near-perfect vacuum, colder and quieter than anywhere that has ever existed on the surface of our world, with an average temperature hovering just a few degrees above absolute zero, around negative 270 degrees Celsius, roughly 3 Kelvin, only a few degrees above the theoretical coldest possible temperature in the universe. This near-total emptiness has one strange consequence that's worth pointing out, because it inverts something we normally think of as dangerous. On Earth, and even within the solar system, dust and debris are the things you worry about. Micrometeorites capable of puncturing a spacesuit or damaging a spacecraft's hull. But true interstellar space is so empty that the risk of collision with any solid particle over even extraordinarily long journeys becomes almost vanishingly small. The danger of interstellar travel was never really about hitting something. It's about the sheer, punishing duration of a journey through a void so complete that there is functionally nothing there at all, nothing to interact with, nothing to mark your progress, nothing but the slow, silent passage of enormous stretches of time. And this is where we arrive at the actual heart of what makes distance itself feel more terrifying the further you travel, because it isn't really about any single hazard. Radiation is real, isolation is real, temperature is real, but none of these things, individually, is the true source of the unease that builds the further out this journey goes. The true source is what all of them add up to together, the total, cumulative loss of every reference point that has ever made a human being feel located, safe, and connected. On Earth's surface, you are protected by an atmosphere, a magnetic field, a temperature range compatible with life, an ecosystem that produces breathable air, and constant, instantaneous contact with every other human being on the planet. Move to low Earth orbit, and you lose the atmosphere but keep the magnetic field, and you keep near instant communication. Move to the Moon, and you lose the magnetic field but keep sight of Earth as a single, whole, comprehensible object, and keep communication delayed only by seconds. Move to Mars, and you lose real-time conversation entirely, communication now measured in minutes, and you lose any meaningful magnetic or atmospheric shielding. Move past the heliopause, and you lose the Sun's protective influence altogether, the last large-scale structure in this entire journey that had been standing between you and the raw radiation environment of the galaxy. Move toward another star, and you lose shared time itself, the assumption that the people you left behind are experiencing the same present moment you are. Each step of this journey doesn't introduce a new monster, it removes an old shield, and that, more than any single hazard we've discussed tonight, is the real reason space gets more terrifying the further you travel through it. It isn't that danger increases like a monster getting closer, it's that safety decreases, layer by layer, like a series of doors closing behind you, each one final, each one making the next open door feel a little colder than the last. The nearest star system to our own is Alpha Centauri, a triple star system located about 4.24 light-years away, or roughly 40 trillion kilometres, about 25 trillion miles. If Voyager 1, our fastest and most distant spacecraft, was somehow pointed directly at Alpha Centauri, which it is not, it would take approximately 73,000 years to arrive, travelling at its current speed. Let that number sit next to something familiar. 73,000 years ago, anatomically modern humans had only recently begun migrating out of Africa. The last ice age hadn't started yet. Agriculture wouldn't exist for another 60,000 years. Writing wouldn't exist for another 69,000 years. That entire span of human history, everything we have ever built, discovered, fought over and created, is shorter than the time it would take our fastest spacecraft to reach the single nearest star system to our own sun. Alpha Centauri is actually a system of 3 stars, Alpha Centauri A and B. A close binary pair, similar in size to our own Sun, orbiting each other roughly as far apart as Uranus orbits the Sun, and a third, much smaller and dimmer star called Proxima Centauri, which orbits the other two at a vast distance and happens to be, at this moment in cosmic history, the single closest star to our own solar system. In 2016, astronomers using the European Southern Observatory's telescopes announced the discovery of a planet orbiting Proxima Centauri, named Proxima Centauri b, orbiting within what's called the star's habitable zone, the region where temperatures could theoretically allow liquid water to exist on a planet's surface. The discovery generated enormous excitement because it meant the single nearest star to our Sun might host a potentially habitable world. But Proxima Centauri is a red dwarf star, smaller, cooler, and far more volatile than our own Sun, prone to violent flares that periodically blast enormous amounts of radiation at any planets orbiting close enough to remain warm. And many astronomers believe those flares may make Proxima Centauri be far less hospitable than its position in the habitable zone alone would suggest. Another example of how a place can look promising from a distance and reveal serious complications the closer you actually look at it. There is one proposal, still in early theoretical and experimental stages, that attempts to sidestep the generation ship problem entirely by making the spacecraft so small and so light that reaching a meaningful fraction of the speed of light might actually become achievable within a single human lifetime. The project is called Breakthrough Starshot, announced in 2016 with backing from a small group of physicists and private investors, and its proposed design looks almost nothing like any spacecraft that has ever flown. Rather than a large heavy probe, the concept involves a fleet of tiny spacecraft, each one a chip only a few centimetres across, weighing a few grams, attached to an ultra-thin sail only a few metres wide. Instead of relying on onboard fuel, these tiny probes would be accelerated by an enormous array of lasers based on Earth, focused briefly but with tremendous power onto the sail, pushing the spacecraft forward through the pressure of light itself, a concept called a light sail, first proposed in a simpler form by the astronomer Carl Sagan decades earlier. According to the project's own published estimates, a laser array powerful enough to do this, an array that does not yet exist and would require significant advances in both laser technology and international engineering cooperation to build, could theoretically accelerate one of these tiny probes to roughly 20% of the speed of light within just a few minutes, after which the probe would simply coast, unpowered, for the remainder of its journey. At that speed, a probe could, in principle, reach Alpha Centauri in a little over 20 years and begin transmitting data back to Earth, arriving here a further 4 years later, meaning a complete round trip of information, launch to first data received, could theoretically occur within a single generation, rather than the tens of thousands of years required by any spacecraft technology that currently exists. The engineering challenges remain immense, and as of now, no full-scale version of the system has been built. The tiny probes would need to survive years of exposure to interstellar radiation and dust impacts at extraordinary relative speeds, since even a microscopic grain of interstellar dust, struck at 20% of the speed of light, would carry enough kinetic energy to seriously damage or destroy a lightweight probe. The receiving equipment on Earth would need to detect an extraordinarily faint signal transmitted by a spacecraft the size of a postage stamp from over 4 light-years away, using a power source barely larger than a coin cell battery. And the laser array itself, according to some estimates, would need to be among the most powerful directed energy systems ever constructed, briefly drawing as much power as a significant fraction of a country's electrical grid for the few minutes each launch would require. Even so, Breakthrough Starshot represents something genuinely different from every other interstellar concept discussed tonight, because it is the first proposal in the history of spaceflight that attempts to reach another star system using physics and engineering that are, in their basic form, already understood today, rather than depending on some future breakthrough in physics we don't yet have. Whether or not this particular project ever launches, it represents a real, serious answer to a question that has quietly run underneath this entire journey. Is there any way, using only what we currently know to be true about the universe, to make the distance between stars survivable within the span of a single human life? For the first time in this story, the answer might, cautiously, be yes for information if not yet for people, because it may genuinely represent one of the only physically plausible ways for human beings to ever reach another star system using anything resembling foreseeable technology. The basic idea is straightforward, and, once you understand the distances involved, almost inevitable. If a journey between stars is going to take hundreds or thousands of years, even at speeds far beyond what we can currently achieve, then no single human crew could survive to complete it. Instead, an entire self-sustaining community would need to launch together, live their entire lives aboard the ship, raise children who would also live and die aboard the ship for potentially dozens of consecutive generations, none of whom would ever see the destination, none of whom would ever have known Earth directly, until finally, generations later, a crew born entirely in transit would arrive at a star system none of their ancestors had ever seen either. It is one of the most quietly staggering ideas in all of space exploration, because it requires accepting that meaningful interstellar travel might not be a voyage a person takes, but a voyage a bloodline takes, spanning centuries, carried forward by people who never volunteered for the journey because they were born already partway through it. Engineers and physicists who have studied the theoretical requirements of a generation ship have identified challenges that go far beyond simple propulsion. A ship would need to be entirely self-sustaining, producing its own food, recycling its own air and water, with close to perfect efficiency over centuries, and maintaining a genetically diverse enough population to avoid the health problems that come from generations of inbreeding within a closed group. A concern serious enough that some studies have suggested a minimum viable population for a successful multi-generational voyage might need to number in the many thousands, far larger than the crew sizes typically imagined in science fiction. The ship would also need some form of governance and culture capable of surviving centuries of isolation without collapsing into conflict or losing its own sense of purpose. A sociological and psychological challenge that may, in the end, be harder to solve than any of the engineering problems involved. Even at speeds far beyond anything Voyager has ever achieved, the numbers remain almost incomprehensibly large. A theoretical spacecraft capable of reaching 10% of the speed of light, a speed no human-made object has ever come close to achieving, and one that current propulsion technology cannot realistically produce, would still take over 40 years to reach Alpha Centauri. At that speed, something else begins to matter. Something Albert Einstein described in his theory of special relativity over a century ago. Time itself begins to behave differently for the travellers than for the people they left behind. As an object's speed increases and approaches the speed of light, time for that object, relative to a stationary observer, slows down. This isn't a philosophical idea or a metaphor. It has been measured directly, repeatedly, using atomic clocks flown on aircraft and satellites, and it is a real physical consequence of the structure of space-time itself. At 10% of the speed of light, the effect is small but real, amounting to a difference of a fraction of a percent between the traveller's experienced time and the time experienced back on Earth. But at higher fractions of the speed of light, speeds that remain entirely theoretical for any spacecraft we currently know how to build, the effect becomes dramatic. A crew travelling at close to the speed of light could, in principle, experience only a few years passing aboard their ship, while decades or centuries passed back on Earth. This is sometimes called the twin paradox. Imagining one twin who stays on Earth while the other travels near the speed of light and returns to find their sibling has aged decades, while they themselves have aged only a few years. It isn't really a paradox at all, in the sense of being a contradiction. It's a genuine, measurable consequence of relativity confirmed repeatedly through real experiments, and it means that a crew travelling at close to the speed of light could step off their spacecraft, still young, into a world that had aged around them without them. A version of Earth that had continued forward through history, while they had, for all practical purposes, been carried outside of its timeline entirely. This is one of the strange, specific ways that space becomes more disorienting the further and faster you travel through it. And it isn't about radiation or isolation at all. It's about identity, about what it means to leave a place behind so completely, for so long, that the very fabric of shared time no longer connects you to the people you left there. A generation ship crew departing today, travelling for several centuries even without approaching relativistic speeds, would arrive to find that everyone they knew, and everyone their parents and grandparents ever knew, had been gone for generations before they even set foot on their destination. Let's take this one final step outward, not because any spacecraft could realistically make this journey, but because understanding the true scale of where we sit is part of understanding why every single thing we've discussed tonight, all 24 billion kilometres of Voyager 1's incredible journey, all 73,000 years it would take to reach the nearest other star, is still an almost immeasurably small fraction of what's actually out there. Our Sun sits inside the Milky Way galaxy, a vast disc-shaped collection of an estimated 100 to 400 billion stars, spanning roughly 100,000 light-years across. Our solar system is located in one of the galaxy's spiral arms, often called the Orion Arm or the Orion Spur, roughly 26,000 light-years from the galactic centre, a region dominated by an object named Sagittarius A, a supermassive black hole with a mass roughly 4 million times that of our Sun. Astronomers confirmed the presence of Sagittarius A through decades of careful observation of stars orbiting an apparently empty point at the galaxy's centre, tracking their orbital paths and speeds with enough precision to calculate the mass of the invisible object they were circling, work recognised with the 2020 Nobel Prize in Physics. In 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A, not a photograph in any conventional sense, but a reconstructed image of the glowing ring of superheated gas surrounding the black hole's event horizon, the boundary beyond which nothing, not even light, can escape. To travel from our solar system to the galactic centre, even at the speed of light, which nothing with mass can actually achieve, would take 26,000 years. To cross the entire visible disk of our own galaxy at the speed of light would take roughly 100,000 years. Our Sun completes one full orbit around the centre of the Milky Way roughly once every 230 million years, a single galactic year, meaning that the last time our solar system was in its current position relative to the galactic centre, dinosaurs had not yet appeared on Earth. It's worth understanding, in a little more depth, exactly what a black hole is, because the term gets used so casually that its actual strangeness tends to get lost. A black hole forms when an enormous amount of mass is compressed into an extremely small volume, so small and so dense that the resulting gravity becomes strong enough to prevent even light from escaping, which is the reason it appears black, and the reason we can never observe one directly, only the effects it has on everything around it. The boundary marking the point of no return is called the event horizon, and for Sagittarius A, with a mass roughly 4 million times that of our Sun, that boundary spans a region larger than the orbit of Mercury around our own Sun. Anything that crosses it, light included, is gone. Not destroyed exactly, but permanently removed from any possibility of ever communicating with, or being observed by, anything on the outside again. Physicists describe what would happen to an object falling toward a black hole using a term that sounds almost playful for something so violent: spaghettification. Because gravity grows so much stronger at close range than at slightly further range near a black hole, the gravitational pull on the near side of any falling object becomes dramatically stronger than the pull on its far side, stretching the object longer and longer, thinner and thinner, until, in principle, it is drawn out into a thin strand, the same way stretching a piece of dough between two hands pulls it into a longer and longer strip. For a supermassive black hole like Sagittarius A, this process would actually happen gradually enough that a falling object could cross the event horizon largely intact, the stretching becoming severe only much closer to the centre. For a smaller black hole formed from the collapse of a single massive star, the same process would happen far more abruptly and far more violently, tearing an object apart long before it ever reached the point of no return. And here, the theme of time distortion that we touched on earlier, with spacecraft approaching the speed of light, reappears in an even stranger form. General relativity predicts, and observations have confirmed, that time itself passes more slowly in stronger gravitational fields, an effect called gravitational time dilation. Near the event horizon of a black hole, this effect becomes extreme. An observer watching, from a safe distance, an object falling toward a black hole would never actually see it cross the event horizon at all. Instead, they would see its motion appear to slow down more and more, its light growing dimmer and more stretched toward longer wavelengths, approaching the horizon forever without ever quite seeming to reach it, frozen from the outside perspective. At the threshold. From the perspective of the object actually falling, none of this delay would be felt at all. It would cross the horizon in an ordinary, finite amount of its own experienced time, completely unaware, in the moment, that it had passed a boundary from which nothing could ever return. Two completely different, equally valid experiences of the exact same event, depending entirely on where you happen to be standing when it happened. It's one of the strangest, most genuinely mind-bending, confirmed predictions in all of physics, and it exists, right now, 26,000 light-years from where you're lying. According to recent analysis of deep field imagery captured by instruments, including the Hubble Space Telescope, and, more recently, the James Webb Space Telescope, which has peered back further into the universe's early history than any instrument before it, capturing light from galaxies that formed within the first few 100 million years after the Big Bang. Light that has been travelling toward us, uninterrupted, for over 13 billion years. The nearest large galaxy to our own, Andromeda, sits approximately 2.5 million light-years away. Even light, the fastest thing that exists, takes 2.5 million years to cross the gap between our galaxy and our nearest large neighbour. To place that number beside something human, 2.5 million years ago, is roughly when the earliest members of the genus Homo were first beginning to appear in the fossil record in Africa, long before anything resembling modern humans existed. The light we would need to travel outward on right now to reach Andromeda, would arrive at a destination whose own light left it before our species, in any recognizable form, had come into being at all. Remarkably, Andromeda is one of the few galaxies in the universe actually moving toward us rather than away, drawn by mutual gravity, and current calculations suggest it will collide and eventually merge with the Milky Way in roughly 4 to 5 billion years. An event so slow, on the scale of individual stars, that it would be almost imperceptible to any observer living through any single moment of it, even though the two galaxies would be visibly merging across the sky over millions of years. Zoom out even further, past individual galaxies entirely, and something else becomes visible, something astronomers only began mapping in detail toward the end of the 20th century, once telescopes and computing power finally became capable of charting the positions of hundreds of thousands of galaxies at once, rather than just a handful at a time. Galaxies, it turns out, are not scattered randomly through the universe. They are arranged into a vast, sprawling structure, sometimes called the cosmic web, enormous filaments and sheets of galaxies, hundreds of millions of light-years long, connected at intersections called superclusters, surrounding equally enormous, nearly empty regions called cosmic voids, some of which span hundreds of millions of light-years across, and contain only a scattering of galaxies, sometimes almost none at all. Our own local group of galaxies, including the Milky Way and Andromeda, belongs to a larger structure called the Virgo supercluster, which is itself just a small part of an even larger structure called Laniakea, a name meaning immeasurable heaven in Hawaiian, chosen by the astronomers who first mapped its full extent in 2014. A supercluster complex containing roughly 100,000 galaxies spread across 500 million light-years. Even Laniakea is being pulled somewhere. Careful measurements of galaxy motion across our region of the universe revealed, decades ago, that the Milky Way, along with thousands of other galaxies, is being drawn toward a region of unusually strong gravitational pull that astronomers have nicknamed the Great Attractor, located roughly 220 million light-years away. Partially hidden from direct observation by the disk of our own galaxy, which blocks a significant portion of the sky in that direction with dust and stars. For years, its exact nature was genuinely mysterious, simply an area toward which enormous numbers of galaxies appeared to be flowing, without a clear picture of exactly what was there. More recent, wider surveys suggest the Great Attractor is itself just a smaller feature within an even larger structure, a gravitational basin that current research suggests may itself be flowing towards something even more massive still, sometimes called the Shapley supercluster, one of the largest known concentrations of galaxies in our observable universe. There's something worth noticing in this, a kind of vertigo that comes not from any single distance, but from the sheer number of times, tonight, that we've reached what felt like the largest possible scale, only to discover it was one small structure nested inside something larger still. The solar system inside the Oort Cloud. The Oort Cloud inside the galaxy inside the local group inside the Virgo supercluster inside Laniakea itself being drawn toward the Great Attractor, and the Great Attractor towards something larger again. At no point tonight have we actually reached the outer edge of anything real. We have only ever reached the current limit of what we happen to be able to measure, and every single time, without exception, that limit has turned out to be another small piece of something even bigger, stretching outward, it seems, for about as far as our instruments have ever managed to look. And beyond even this, beyond the cosmic web, beyond every supercluster and every void, space continues to expand outward in every direction. And here we run into one of the strangest and most genuinely humbling facts in all of modern cosmology. The universe is not just large, it is expanding, and that expansion is accelerating, driven by a poorly understood phenomenon that scientists call dark energy, believed to make up roughly 68% of the total energy content of the universe. Even though we still do not have a complete physical explanation for what it actually is. Because of this ongoing expansion, there exists a boundary, calculated by cosmologists, beyond which galaxies are receding from us faster than the speed of light itself, not because they are physically moving through space faster than light, which nothing can do, but because the space between us and them is stretching so rapidly that the distance grows faster than light can cross it. Light from those galaxies emitted today will never reach us. Not in 1,000,000 years. Not ever. There are galaxies existing right now that we will never see, never detect, never have any way of confirming, because the universe itself has permanently placed them beyond our reach. Of the estimated 2 trillion galaxies in the observable universe, cosmologists calculate that the overwhelming majority, somewhere in the range of 97%, are already forever unreachable, their light already receding from us faster than we could ever catch up to it, even if we could somehow travel at the speed of light itself. This means that the observable universe, the roughly 93 billion light-year wide sphere of everything we can, in principle, ever detect, is not the whole universe at all. It is simply the portion of it that light has had time to reach us from, since the beginning of the universe roughly 8 billion years ago, and it may represent only a small fraction of a universe that could, according to some cosmological models, be far larger, or even infinite, extending endlessly in every direction beyond the boundary of anything we could ever hope to observe. There's one more layer to this that's worth understanding, because it reaches even further back than any galaxy we could ever hope to see. When astronomers point sensitive instruments at seemingly empty patches of sky, in every direction, they detect a faint, uniform hiss of microwave radiation, coming from everywhere at once, with almost no variation from one direction to another. This is the cosmic microwave background, first detected accidentally in 1965 by 2 researchers at Bell Labs, Arno Penzias and Robert Wilson, who initially suspected the strange, persistent noise in their radio antenna was caused by pigeon droppings, before realizing they had stumbled onto something far larger, the faint afterglow of the universe's own infancy. The cosmic microwave background is, in effect, the oldest light that can ever be observed, radiation released roughly 380,000 years after the Big Bang, when the universe had finally cooled enough for light to travel freely for the first time, rather than being scattered instantly by the dense, hot plasma that filled all of space before that moment. It surrounds us in every direction, a wall of light so old and so uniform that it effectively marks the outer boundary of anything we could ever, even in principle, observe using light itself. Beyond it lies an earlier universe, opaque to light entirely, that we can only study indirectly, through theory and through faint traces left in the light we can see. This means that even the boundary of the observable universe, the roughly 93 billion light-year sphere we discussed a moment ago, isn't really the edge of space in any physical sense. It's the edge of what light has had time to show us, a boundary defined by time rather than distance, receding further outward every single day as more light, from ever more distant sources, finally completes its multi-billion-year journey to reach us. In a strange sense, the universe hasn't finished revealing itself to us yet, and won't ever finish, because there will always be more light still in transit, older and more distant than anything we've seen so far, arriving a little at a time, forever. And it's worth asking, gently, where all of this eventually leads. Because the story of distance we've told tonight has a natural continuation in the story of time. Current cosmological models suggest that the accelerating expansion driven by dark energy will continue and very likely intensify for the indefinite future, over spans of time that dwarf even the numbers we've already discussed tonight, trillions upon trillions of years. The universe is expected to grow cold, dark, and increasingly empty as galaxies drift beyond each other's ability to ever interact again. Stars exhaust their fuel and wink out one by one, and matter itself, according to some theoretical models, slowly decays into its most basic constituent particles. Physicists refer to this ultimate, far-future state as heat death, a condition in which energy has spread out so completely and so evenly that no meaningful work, no stars, no chemistry, no motion of any interesting kind can ever occur again. It is, by most current calculations, less something that might happen and more something that will happen given enough time, unless something about our current understanding of physics turns out to be fundamentally incomplete. This isn't meant to unsettle you before we close out tonight. If anything, it's meant to do the opposite, because sitting next to a number that large has a way of making the ordinary, finite, fragile present feel more vivid rather than less. Whatever is coming, trillions of years from now, has no bearing at all on the fact that tonight, right now, the sun is still warm, the atmosphere is still breathable, and the small, improbable planet you're lying on is, for the moment, exactly as alive and as lucky as it has ever been. This is the true edge of the journey we began tonight, in low Earth orbit, 400 kilometers above the surface, where the International Space Station quietly circles the planet every 90 minutes. From there to the moon, still close enough to see whole. From there past Venus, the most lethal surface in the solar system, despite being one of our nearest neighbours. From there to Mars, where a conversation takes 20 minutes each way, and where entire weeks disappear into radio silence during conjunction. From there, past the strange emptiness of the asteroid belt, to the outer planets, where deadly radiation belts dwarf anything Earth has ever produced, and where an ocean world like Europa hides some of the best odds for life anywhere beyond our own. From there, past the tilted, howling ice giants Uranus and Neptune, worlds visited only once, decades ago, and never revisited since. From there, past the heliopause, where the sun's protective influence ends, and the true radiation of the galaxy begins, carrying with it 2 golden records that will likely outlast every trace of human civilization on Earth. From there, through the almost impossibly vast Oort Cloud, which our fastest spacecraft will take 30,000 years just to clear. From there, toward Alpha Centauri, 4 light years distant. A journey that would take our fastest current technology longer than the entirety of recorded human history to complete. From there, outward to the edge of our own galaxy, 100,000 light years across, orbiting a black hole 4 million times the mass of our Sun. From there to Andromeda, whose own light is older than our species. And from there, finally, to the edge of what can ever be seen or reached at all, a boundary defined not by our technology, but by the expanding structure of the universe itself. A boundary beyond which 97% of everything that exists has already slipped permanently out of reach. Here is the humbling truth this entire journey has been building toward. Every single human being who has ever lived, every war fought, every book written, every love story, every discovery, every sunrise anyone has ever watched, has taken place entirely within a space smaller than a single pixel on a map of our own galaxy, which is itself one of 2 trillion galaxies, the overwhelming majority of which we will never see, contact or reach. Not because we haven't built the right spacecraft yet, but because the universe has permanently placed them beyond the boundary of what light itself can ever cross to reach us. And yet, within that impossibly small, impossibly specific point in an impossibly vast universe, there exists a magnetic field strong enough to deflect lethal radiation, an atmosphere thick enough to breathe, a temperature stable enough to sustain liquid water, and a sun close enough to provide warmth without destroying everything it touches. Every layer of protection we discussed leaving behind tonight, the magnetosphere, the atmosphere, the heliosphere, the shared timeline of a single planet's history exists right now around you as you listen to this. Not because the universe designed it that way for us. As far as we understand, none of it was designed at all. It is simply where we happen to be, an almost unimaginably rare alignment of conditions, sitting quietly at the exact centre of everything that has ever mattered to us. In a universe that is, everywhere else, colder and darker and further away than the mind can really hold on to for very long. Carl Sagan, looking at that single photograph of Earth taken from nearly 6 billion kilometres away, once reflected that everyone who has ever lived out their lives on that tiny point of light suspended in a sunbeam. And that, in some ways, the very smallness of it, was the most convincing argument he knew of for taking better care of one another, because it was, as far as anyone has ever been able to determine, the only home we have. It's worth remembering as we close that everything frightening about tonight's journey was never really about space itself. Space is not hostile in the way a storm or a predator is hostile. It has no intention at all, no malice, no awareness that we exist to be threatened by. Every hazard we trace tonight, the radiation, the pressure, the silence, the isolation, the slow drift of shared time, was simply the ordinary, indifferent physics of a universe that was never built with a human body in mind. What made each stage of that journey feel more terrifying than the last wasn't an increase in danger reaching out toward us. It was the steady loss of the very specific, very narrow set of conditions we happen to need, conditions that exist, as far as we have ever been able to find, in exactly one place. That's where we'll leave things tonight, not at the edge of the observable universe, not among the 97% of galaxies we will never reach, not drifting through the cold, thin plasma beyond the heliopause, but back here, on this small, warm, shielded, impossibly fortunate world, where the magnetic field is still holding, the atmosphere is still breathable, and the sun is still exactly close enough. Somewhere above you, right now, that field is quietly doing the same work it has done for billions of years, deflecting a wind you'll never see, so that you can rest, undisturbed. Tonight, rest well.